The most common elementary interpretation of a definite integral is that of the area under a curve. To be more precise, when a function has positive and negative values, the integral is the signed area between the curve and the x-axis, where area above the x-axis is positive and area below is negative. Our goal now is to use parameterizations to find areas of more general regions, such as this one, that are not just bounded above by a given curve. Let's start with a simpler case, though, of a curve such as this one that we saw earlier, that can be parameterized by x equals x of t and y equals y of t, but passes the vertical line test and therefore can be considered as a function of y in terms of x, say y equals f of x. Then we know that the shaded area equals this integral. With the substitution, we see that this is the same as this integral in terms of t. We are letting alpha denote a value of the parameter that gives us the left point of the curve, and likewise beta a value larger than alpha that gives us the right point. We are also assuming that x and y are continuous functions of t. To see how we can extend this approach to a curve such as this one, let's make two assumptions about the curves we consider. First, they should be closed. Second, they should not intersect themselves. There's one notion that we need that exists in a certain sense in the original development of integrals as areas under curves, and that is that the direction in which we trace the curve imparts a sign to the area. For example, this integral represents the shaded area, while this one represents the same area with the opposite sign. In the first case, we imagine tracing the curve from left to right, while in the latter, we imagine it being traced from right to left. The sign changes because when we flip the limits of integration, we're switching the signs of all the delta x terms in the Riemann sums, which changes the sign of the integral. In the context of a closed curve, we impart sign independent of the relationship between the curve and the x-axis. Rather, we impart a sign based on a declared orientation. The counterclockwise orientation is declared to be positive, while the clockwise orientation is declared to be negative. Thus, our approach to finding area depends in part on how we parameterize the curve. Let's see how to find the area of a closed curve using a parameterization by looking first at a simple example. Let's consider this curve with positive orientation. We'll see soon that it's the convexity of the curve that makes it a good starting point. Suppose that the leftmost and rightmost x-coordinates are a and b, that t sub 0 is a value of the parameter that corresponds to the right point, t sub 1 is the smallest value of t larger than t0 that corresponds to the left point, and t sub 2 is the smallest value of t larger than t1 that corresponds once again to the right point. Let's see how we can get the area within the curve. We'll do this by finding this blue area and then subtracting this red area. First, we know that this area equals this integral from t sub 0 to t sub 1 multiplied by -1. We need the -1 because we are moving from right to left along the x-axis. Similarly, the red area equals this integral from t sub 1 to t sub 2. We don't need a -1 term because this time the curve is being traced from left to right. To find the area within the curve, we find the difference of these integrals. But these combine to form this single integral, which gives us a remarkably simple formula for a potentially very complicated area. We can use similar reasoning to extend this to a non-convex shape, even one that has corners or cusps, as long as we assume that there are only finitely many lines as pictured here, called lines of support.